Assalamualaikum warahmatullahi wabarakatuh. This is a pre-recorded video on the um, second example of the rectifier, DC motor drive by using rectifier circuit. Okay, so this is the example. I think this example is from your previous final exam, I think. Okay, so a rectifier DC motor drive is supplied by a three-phase full control SCR bridge, and the supply is 240 volt RMS, 50 Hertz. This one is a per phase, meaning that this is 240 volt is actually a phase voltage. Okay, and the field circuit is supplied by a single phase. Okay, not three phase. The field circuit is supplied by single phase, 240 volt RMS, 50 Hertz also, with control bridge rectifier. Okay, so the field current IF is set as maximum as possible. Okay, the separately excited DC motor has characteristic of this, which is the armature circuit RA, RF, and is also given the motor constant. Assume the inductance of the armature and field circuit is large enough to ensure continuous and ripple-free currents. If the delay angle of the armature converter, which is your firing angle, alpha A, is 45 degrees, and the required armature current is around 30 ampere, so calculate the developed torque, okay, the speed of the motor, and C, which actually we will discuss later. So calculate the developed torque. Okay, so actually this is the, I draw all the information here. So this is the armature circuit here, and this is your field circuit. So both circuit, rectifier, three phase, but the field circuit is a single phase. Okay, and the firing angle is 45 for the armature circuit, but for the field circuit, it said that the field current is set as maximum as possible. So from this sentence, it actually indirectly, we can say that the alpha of the field circuit is 0. Because we know that when you delay the angle, the value of the voltage and also the current will be lower, okay? So maximum meaning that there is no delay, okay? So an IA that flow inside the armature is given as 30 ampere. Okay, so calculate the developed torque, okay? So we know that the torque developed is KT, IF, and IA, and usually, okay, usually KV, which is your motor constant, which is always referred to the back EMF here, sometimes or usually is equal also to the torque constant. Okay, so right now it has been given 1.5, therefore need to find, okay, so therefore need to find only the IF. Okay, so the field current here, as you can see, the IF can be obtained by using Ohm's law, okay, from the field circuit here. So IF is equal to VF over RF. And so this is a single phase, so full wave. So the equation for the single phase full wave continuous conduction mode, which is 2 Vm over pi cos alpha, but alpha is 0. So, and then over your RF 175 ohm, so you will obtain your IF is 1.235. Okay, and then after you have found it, is actually you can actually calculate your torque developed by the motor by using this equation. So KT is 1.5, IF is 1.235, and IA is given 30. So the torque developed by the motor is around 55.56 Newton meter. Okay, and what about the speed of the motor? The speed of the motor, okay, the speed of the motor is given as always can be obtained from this equation. the back EMF, because the only equation that relate the speed and the circuit is actually the back EMF equation. Okay, so you can find this, but right now you don't know what is the value of the EA, okay, back EMF. But back EMF can always be obtained by using the KVL loop from the armature circuit. So EA is equal to VA or minus IARA. Okay, and VA is actually the output from the rectifier. And for the armature circuit, the rectifier used is a three-phase rectifier circuit. So three-phase rectifier circuit control. So this is the equations. Okay, T3 multiply VM line to line cos alpha over pi. And since the given is actually a P phase and also RMS, so you need to convert the RMS and also into a line to line. So by multiplying square root 2 and square root 3. And alpha is given as a 45 degrees. And finally, you will obtain your VA is around 397 volt. Okay, so you obtain this one, and IA is given, which is 30 ampere, and RA is also been given. Okay, then finally, this is your IA, and then this is your RA. So you will have your back EMF is 388 volt. Okay, and by using the back EMF equation, so this is your KV multiplied with your IF 1.235. So you will obtain your speed is around 209 radian per second. Okay, so we have complete A and B. Okay. Okay, so right now let's see on the last questions. So the last question is, I think, the most interesting part in this example. If the polarity of the field current is reversed, okay, the motor back EMF will reverse. Okay, why? Because as you can see here, the equations, back EMF and also IF here. So if IF is reversed, meaning that negative value, the same will goes to the EA. So EA will also have a negative value, a reverse values, okay? So for the same armature current, which is a positive 30 ampere, so determine the required delay angle of the armature converter. Okay, so if it's reverse, so automatically the back EMF will have a negative value, the same value, but revert with a negative value, 388 volts, and the armature current is same. So you use the back EMF, you use the the circuit, the KVL of the armature circuit like this. Okay, IA is using the same 30 ampere multiplied with the RA minus the EA. You will obtain the value is negative. Okay, 379 volts. Okay, and so this is a three-phase rectifier circuit output. So you need to use this one. The equation for the three-phase. So 3 multiplied square root 2 multiplied with square root 3 multiplied with 240 volt RMS multiplied with cos alpha. Then you will obtain that alpha is 132.5. Okay, I would like to highlight that for the rectifier circuit, either whether it is a single phase or three-phase, if the angle of the firing angle is higher than 90 degrees, you will obtain your voltage output is a negative value. Okay, so to maintain your voltage at the positive value, please always make sure that your alpha is not larger than 90 degrees. Okay, so I think that concludes the example 2. Thank you very much.